This lecture is about the linear momentum equation. We got the linear momentum equation identified last time and talked a bit about it. Maybe it could be said this is about applying the linear momentum equation. So the linear momentum equation is used in fluids, in particular chapter 5, allows us to figure out this thing right here. So let me try to, you've seen that before in some form. Let me try to describe what that means. CV is the symbol for a control volume. So that's some sort of region in space, like over here. And usually it's the inside of, or the interior of some sort of device. Not always, but many times it's an interior device, something like a fan, the interior of the fan, okay? The net force on the control volume, many times it's useful to say, hey, that's the force on the fluid inside the control volume. So in a case like this, when this fan is running, of course, there's always fluid in and always go fluid out. So when we actually compute this thing, the net force on the control volume, let's say it turns out to be 30 pounds to the right, okay? That's the force on the molecules, the fluid molecules in the control volume at any sort of instant. In ME120, we do steady state. So the number of molecules inside that control volume are the same, and what's going on with them is going to be the same continually. So we would say that basically when we do this computation, you might say, hey, 30 pounds is the force on the molecules at an instant, but that 30 pounds is going to be there continuously because we're in steady state. Hey, before we get going more on this, why go to all this work on working out on determining the net force on the fluid particles in the control volume? And many times it's for purposes of figuring out other forces. That's what we're going to work on today. So to take this example, I wish I could set this up and really get this going. If I take this fan and put it on a smooth surface, it actually will start going backwards. And you can pretty clearly think about why if you think about Newton's third law. If this fan were exerting a force of 30 pounds on the air that way, by Newton's third law, there would be a force of the air on the fan the other way. And so then that means as a reaction, the fan would go backwards. Well, you see that sometimes where a fan is poorly anchored and it kind of leans backwards or even scoots backwards. Our job as engineers, if we were designing some sort of air moving system, would be to anchor this fan sufficiently, and coming up with this force is helpful. How about something like this, okay? Just a simple sprinkler where we're gonna have water come in here like this, and then the water's gonna go up, okay? Well, how about the force on the control volume? That would be the force on the water inside the sprinkler. And we might think about horizontal force, and we might think about vertical force. Right now, I'm just going to think about horizontal force. Okay, well, the water comes in here really, really fast through a hose, and then bang, it hits this side here and stopped, and instead goes up. So what is the net force on the water? Okay, horizontally, the net force on the water is backwards like this. It stops that horizontal motion. So force of sprinkler on water that way, conversely force of water on sprinkler that way. And this, it's possible if this thing weren't anchored, that would end up, and we're on a smooth surface, that it would end up scooting like that. Well, we anchor it. How much is it going to take to anchor it? Well, it's helpful to know those forces, and that's why we do that calculation. All right, so reminder, statement of the linear momentum equation. Hey, the net force on the fluid in the control volume is going to be, we can calculate it by taking a look at the difference between the linear momentum flow out, which is that number right there. We get momentum flow by doing m dot times velocity, where velocity is a vector, okay? And minus m dot vn, and that's in general how we do it. There may be multiple flows in or out, so that's what that summation symbol indicates. You're going to see that in almost all the problems we're going to do, we're just going to have one fluid stream in and oftentimes just one fluid stream out, or something equivalent to that. So a lot of times it's going to come out something like that. Sometimes we'll do directional. So let's say if all we are interested in is x direction flow, how could we actually write this? Well, M dot is not a vector, so that's not going to have direction. Okay, but we would be interested in the flow in the x direction. And as we saw last time working in chapter 4, sometimes the flow in the x direction is indicated by U. So I'm going to do O for out here, okay? And it would be the difference between what goes out and what's going in. So minus M dot in, U in. And I'll maybe flesh that out a little bit. So this could be termed an x direction for the linear momentum equation. Sometimes all we see, everything that's going on is in the x direction. Not a big difference between these two, but we'd like to be versatile and recognize this when you see stuff in, say, a solutions or in a textbook. And obviously we could do the y direction as well. The net force on the fluid in a CV fluid in a control volume in the y direction. Well, in the y direction, we use for velocity in the y direction, we use v. So it would be m dot v out minus m dot v in. Okay, I think when working with this stuff, writing down these equations is helpful, but getting going on some examples really makes a difference. Hey, today, besides talking about the linear momentum equation and how to apply it, I also want to talk a little bit about efficient problem solving. I'm working on getting quiz 1 to you. I'm sorry that that has fallen by the wayside as I've tried to keep up on lectures. But I have talked to a few of you, and some of you really indicated that you felt the time pressure, and I've had discussions with that issue with students over the years. One thing that I want you to really, for those of you who did feel time pressure, I really want you to focus on for Tuesday's test 1 is when you see a problem, avoid copying everything down word for word. Try to do things symbolically. As in, if it says pressure, the pressure is 20 psi, I think it's a waste of time on your paper to write out the pressure is equal to 20 psi. I think just writing P equals 20 psi at the relevant location is a great thing to do. So this first problem is a nozzle problem. We're just going to do part A. It's a horizontal nozzle. So there's a picture of a horizontal nozzle. Okay, a horizontal nozzle would usually have an inlet pipe. Remember, I mean, hopefully you're aware of this, that a nozzle usually has an inlet pipe and then narrow, so it speeds up fluid. We're only going to do part A of this problem, where we're going to try to apply the linear momentum equation. But what I would like you to do is, I'm going to go to share screen and put up the problem written out, and I would like you on this picture to, as succinctly as possible, write down the relevant information and then get going on part A. So going to share screen. Go for it. You're going to write down the information, okay, as much as possible in symbolic form. And one thing I can see when I'm evaluating students' work is the more problems you do on homework, the more you try to get through this stuff on your own, the better you get at translating things into symbolic form, and that can be very helpful for solving. So I'll read it out loud. 0.5 meter cubed per second of water enters a horizontal nozzle. The nozzle has inlet diameter 10 centimeters, while the nozzle outlet diameter is 5 centimeters. The water gauge pressure at the nozzle inlet is 40 kPa. Assume steady flow, and A is use the linear momentum equation to determine the net force, magnitude, and direction on water in the nozzle. Hey, go. I'm going to go back and pause the video, so hopefully you can go back to this point yourself and pause and take a look at it. I don't want to chew up a lot of time. Okay, you wouldn't need to do it this way, but this is not bad what I have on the board. 0.5 meters cubed per second, what symbol is that? Q. Why is it helpful to write it down in symbolic form? Well, hopefully you have your equation list all there as you take test 1, and some equations will have Q in it. If you need to do something with Q, well, you can then look and see, are there equations with Q that get what I want? Okay. Secondly, one of the major things I'm looking for in the problem solving is, can you identify the relevant equation? Well, this case, I made it easy because I told you which equation to use. So there it is, identify the relevant equation. Trying to keep away from getting flustered and instead be systematic, we're supposed to calculate this y-x direction. Well, it's all horizontal. So hopefully you can see that we have 1, 2, 3, 4 things to calculate, okay? And then we're gonna pause and see if we can figure out those 4 things. And I will let you guys get going working on that. Hopefully you have your equation list out. How do I figure out m dot? How to figure out u? I've been talking to a few of you about how you're feeling while, say, taking a quiz that I gave or a test. And I feel like I made sense to some of you that if you do the homework with the solutions in front of you, you bypass the crucial, the main crucial step on all this. So in this case right here, the main crucial step in getting going on this is we need m dot. Well, what equation do you need for m dot? You look at the solutions, it tells you what equation to use. Your job to get ready for the test is to decide what equation to use. I'm going to pause and see if you can figure out those 4 things. Okay, you could do this in any order you want, but I started by figuring out m dot over here like this. I have Q, volumetric flow, and one equation you should have on your equation list is mass flow rate at entering or exiting something is equal to volumetric flow rate times density. Density of what? Density of the fluid. Water, we would use the standard value in this case. I didn't state it explicitly, but we could use it, and that's 1,000. So I would do 1,000 times 0.5. Hopefully I can see in my head that 1,000 is going to be kilograms per meter cubed. So those meter cubes are going to cancel, and I'm going to get 500 kilograms per second. Wow, this is a big nozzle. All right. Again, I said I have four things I need to figure out, okay? How about, let's do m dot out. How about the mass flow rate over here, m dot out? What is that going to be? Well, remember chapter 5, our first section was about steady state flow for control volumes, okay? Maybe I'll be a little bit like the book and make the control volume the interior of this nozzle here like that, where I have dashed lines, okay? And for steady state, mass flow in is equal to mass flow out. So this is also equal to m dot out, okay? So I have 3 out of 4. I got 2 out of 4. I've got m dot in and I've got m dot out. Now I have to figure out u in and u out. U is essentially just horizontal speed. So see if you can figure out an equation to work out that. Another one of our basic equations is that volumetric flow rate, which we have, is equal to V times A. So once again, if you wrote this symbolically and you know you're looking for speed, hopefully your mind would be thinking, hey, I got volumetric flow rate. What is an equation that has both volumetric flow rate and speed in it? And that's that equation right there. Solve it for speed. It's volumetric flow rate divided by area. This would be a pipe. A nozzle is circular usually at the inlet and the outlet. So the cross-sectional area would be pi d squared over 4. And then hopefully we can plug and chug and work our way through it. This was 10 centimeters, so we would want to convert it to meters so that the units end up canceling. So I'm just going to write that up there, even though you guys know it. That's 0.1 meters. And we're going to get a really, really large speed. Be doing it yourself, and let's see if you match my number. Okay, I got 63.66 on my calculator, but I'm going to pause for a second and check it because obviously that number is going to affect our future work. Okay, it worked for me. Hopefully that's working for you as well. So taking a look at, we're trying to figure out the net force on any water in this nozzle, okay? And that's what the linear momentum equation says. We've got both m dots, okay? We have u in 63.66, and then u out is going to be huge. U out is going to be huge. How can we go about doing that? Well, U out is speed. So basically we're trying to figure out speed coming out here. We're trying to figure out the speed coming out there, all right? And do we have an equation for speed for fluid if it passes through an opening? And absolutely, there's Q equals V over A, okay? And there's also M dot equals rho V A, okay? So we could end up using either one of these equations. I'm going to do it this way. Text tends to do that. And here's the reasoning, okay? Water is incompressible, so that means that it's going to be true that the mass flow rate in and the mass flow rate out are going to be the same. So basically M dot N, you don't need to write this down, but M dot N is equal to M dot out. M dot is density times volume flow. If those densities are the same, then these Q's are the same. Qn is equal to Q out. So basically I could say V1, at the outlet, volume flow at the outlet, if I call this Q2 and I call this Q1, V2A2, because volume flow is V times A, is equal to V1A1, okay? And then I can do the math and solve for V at the outlet. So V at the outlet, sorry, let's get a little bit tight here, but we'll finish it off. V2 at the outlet is equal to V1, okay, times A1 over A2. And just thinking about that for a second, we've got V1, that's the 63.66. We can calculate A1, that's based on the 10 centimeters, and we can also calculate A2. But remembering how we would do this, we've done this sort of calculation before. This is pi d squared over 4, and this is pi d squared over 4. The pi's and the 4's go away, so we could actually calculate this. I'll do this down below. This is going to be V1 times D1 squared over D2 squared. Okay? And we can even be a little bit slicker about it. If we have something squared over something else squared, we could just write it as a single square. Okay, and I'll pause for a second and see if you can get the number yourself. It's going to be huge, by the way. So I forgot to pause, that's okay. 254.6 meters per second. And it's 4 times as big. Hopefully you saw the map that actually worked out that way. Okay, good. So I'll go ahead and cloud that. And then we're gonna finish it off. Okay. Sorry, the board's getting a little bit dense, but we're almost there. Okay. Okay. Why did we do all this? We're trying to find the net force on the water. If you recall, actually, this problem said magnitude and direction. So net force, okay, in the x direction is going to be m dot u out minus m dot u in. We can save ourselves for some work because m dot out and m dot in were the same, so we could factor that m dot out. So we could do m dot times u out minus u in, okay? M dot we got was 500 kilograms per second. I'm going to be a little bit lazy about the units. U out was 254.6. U in was 63.66. Okay. And now I can just do my math, round reasonably, and think about units and direction. Huge number, 95,494. But by the way, this is just a huge flow. It doesn't look like a big number, but half a cubic meter is a lot of water, and that's a lot of water per second. Okay, then what first of all, what kind of units does that have? So this is kilograms per second. This is meters per second. So that gives us kilogram meter per second squared. And as we noted last time, that's a Newton. And we're using this equation to figure out force. So it'd be 95,494 Newtons. Okay, and then what direction? What direction? Okay, well, we have more out than in. Out is to the right, in is to the right, more out than in. The net is going to be the right in the positive direction. So this water, it goes through there, it speeds up. There must be force on it to the right to speed it up. Where does that force come from? We haven't addressed that yet. But the net force on the water is 95,494 Newtons to the right. All right, so another problem where we use the linear momentum theorem. So I'm going to get the problem up on the board in just a second, but this problem is about a T that's in a piping system. So there would be, this is going to be the inlet of the T right here like this, okay? And then obviously in a T, whatever fluid comes in is going to split with some going to the left and some going to the right, all right? And what I want you to do is, again, try to be efficient. While I'm talking now, try to get a drawing, a reasonably sized drawing of a T, not huge and not so teeny that you can't get the information on it, and try either on this T itself or next to it or below it, really, really clearly and succinctly get the information provided. So I'm going to go to share screen. Okay. And all we're doing here is part A of this problem, okay? 30 cubic feet per minute of SAE engine oil enters a T, oil splits, the pressure gauge at the oil inlet reads 30 PSI, 6-inch inlet diameter, outlet diameters are 4 engines, assume steady flow. And part A, actually, I'm sorry, we're going to do part A and part B. We're going to use the linear momentum equation to determine the net vertical force on oil in the T. And then we'll do part B as well. So for right now, you're just trying to get the information down, and I'll be doing it myself. I'm going to go pause the video from running. So I would encourage you guys to pause right now so you have this in front of you and write down the information. Well, here's some stuff I did. I got the flow, and it was 30 cubic feet per minute, but we oftentimes do things for calculations per second. So I changed that to 0.5 feet cubed per second, 6-inch inlet, 4-inch outlets, 30 PSIG at the inlet. Well, it asked the problem, if you recall, asked us to work both vertically and horizontally. So I assigned a coordinate axis, and I'm going to say up is the Y direction is up, and the X direction is to the right. Okay, what most textbooks would call this doing a control volume. Okay, and so I did a dashed line which represents the interior surface of this T where the oil is, and I have flow in here and flow out there like that on either side. Where I didn't note it, but the flow split evenly, it said. Okay, we're going to work in the Y direction. So I want to show that I know what's going on. I wrote down the linear momentum equation in the Y direction. You don't need to use this symbols. You could say Vy out and Vy in. Okay, and hopefully you're thinking, okay, I need 1, 2, 3, 4 numbers, and start working on getting those numbers. I'm going to pause for a second, and then I'll start talking you through it. Well, we'll get to going on the numbers in a second. It's also worth noting when you do these problems to check your intuition. So what if we had a T here like this and oil's running down here like that? And if you recall the question that is asked in part A, hey, what is the vertical force on that oil that comes down here like this? Well, I mean, hopefully it's pretty intuitive that as this oil goes down, this bottom section of the T stops it. So it's pushing up on the oil just to, in a sense, to keep it from flowing down. So we should get a force up. The net force in the Y direction on the oil is up. All right, so talk a little bit about how we're going to go through this, okay? Let's take a look at the picture, all right? These are all vertical. If we're in the vertical direction, they're all vertical. Do we see any vertical flow out of this control volume? And the answer is no. So even though sometimes these problems look intimidating, hey, this is really simple. We don't see any flow out, so we don't need to do that. Do we see any flow into our control volume? Absolutely, we see that right there. So we've got 2 things to calculate. we've got to get m dot and we've got to get the vertical velocity in, and I'll be doing that. Make sure you get that worked out yourself. Okay, so we want to get m dot, and one of the relations, this value given right here is the volumetric flow rate Q. So we can get m dot by doing density times Q. Okay. The density, we would look it up for standard engine oil is 1.77, water's 1.94, oil floats on water, its density is a little bit less, and then we multiply it by 0.5, okay? And we're gonna get something like 0.86, but I'll do it myself really quickly to make sure. That may be a little bit off. 0.885, 0.885. Okay. And what units is that? So another thing that can help you out as you do something like test 1 is if you're doing your homework, you try to work out the units yourself. After a while, that becomes quick. So this is slugs per feet cubed. And this is feet cubed per second. And so it's what we want. It's mass flow rate, it's slugs per second. Okay. All right, now I need to get the, by the way, this was in, now I need to get the vertical velocity in. So the vertical velocity in, how am I going to get that? Well, I can get the speed, okay? I can get the speed by using, again, that equation that volume flow rate is average speed times cross-sectional area. And we use that a lot this semester. So the speed in is the volume flow rate in divided by the cross-sectional area in. And once again, that area is a circle, so it's going to be pi d squared over 4. We would like to convert this diameter to feet. 6 inches is a half feet. So getting the numbers up there, we're going to have 0.5 feet cubed per second divided by pi times 0.5 feet squared all over 4. And we'll crank our way through that and see how that turns out. Okay, so the speed at the inlet is 2.546 feet per second. These numbers are turning about a little bit more reasonably than my previous example. All right, trying to finish it off. We still don't have a force. We're trying to figure out the net vertical force on the oil in here, net vertical force. So this is just a speed, but remember this m dot v is a vector. So we might want to think, what direction is m dot v? And it is down. So m dot v in, breaking it down a little bit, would be a negative number because it's down. So I'm going to write that out really quickly. Negative 0.885 times 2.546. I can do those just on my calculator just by looking at it. 0.885 times 2.546, and I get 2.254. I'll just do it as negative 2.254. And once again, with some practice, you're going to see this. I've got a slug, I've got a foot, and the denominator I've got 2 seconds, and that's a second squared. Slug foot per second squared is a pound. Okay, and again, why negative? The momentum flow in is down, and that's in the negative direction. So let's finish it off then. The net force in the y direction, okay, is going to be equal to 0 minus this negative 2.546, and I get 2.546 pounds. Okay, and there's our answer, that on the oil, there has to be 2.5 pounds of force up, okay, in order to essentially stop the oil flowing and getting it going horizontally. All right, so there's part A. Let's take a look at, I'll just get part B up there. Part B was to figure out the net force on the oil horizontally. The net force on the oil horizontally. So try to write the appropriate linear momentum equation. I'll be doing it myself. Okay, so before we do it, it might be worth looking at it. Okay, in a situation like this, okay, the oil is going to push down on the T. Is it going to push on the T left or right? Or a similar way of thinking about it, is there going to be a net force on the oil to the right or to the left? Well, I'll be interested, if I were talking to you, I'd be interested in your intuitions. Well, let's go through the math. There's the equation we would write. Okay, We got 4 things to figure out. Strictly speaking, if I was being thorough, I would put a summation sign. We're going to add up all the m.u's outs, and we're going to add up all the m.u's ins. So let's talk about the ins horizontally. If you look horizontally, is there any flow in? No, there's no flow in. So hey, this problem looks pretty intimidating, but it's not that bad. Are there any flows out over here like this? And yes, there's a flow out this way and a flow out that way. It looks like we got some work to do, but if we're smart about it, we can just get it done in all very, very quickly. It was stated that the flow splits, okay? So there's going to be an m.u this way, and there's going to be an m.u that way. The flow splits, so half of it goes this way and half goes the other way, okay? The outlets are the same diameter, so the u's are going to be the same, okay? And so as a consequence, these 2 numbers are going to be exactly identical and opposite. They'll cancel out, and we get the net force in the x direction is 0 pounds. And that does it for that part. All right, so that's part of what we want to be able to do with the linear momentum equation, and we'll get back to extending it to make it a little more practical a little bit. But if I could talk again, I talked last time briefly about test 2. Test 2 on Tuesday. The schedule says Monday, but given what's been going on, I wanted to delay it for a day. And I talked last time about the 4 possible free response, which you might call free response or long answer questions. But there are also going to be some quick, what we could call quick hitters. So those are brief problems where you work out the numerical answer and put it in the blank, put it in the box on Canvas. Those are really good practice for you guys who want to take the FE exam or eventually the PE exam. You know, it's either right or wrong, and I'm trying to write those so that they are quick if you know what you're doing. So I talked last semester with a few students. I wish I could have been able to talk to everyone about, hey, how do you handle stuff like that? And one thing we want you to do, obviously in engineering, is really get good at the following process, okay? And the process is something like this. If you have a problem, you want to write down your givens with symbols and your want with symbols. Why is it helpful to do it with symbols? Why, instead of writing down for my want here, writing out force equals, why is it useful instead to write down F equals question mark? Well, the reason that's helpful is you're going to be many times you're going to go to an equation sheet and you're going to be, that in a sense tells you, hey, I need to look with something with F in it. Now, look, you don't need to follow this process. If you see how to do a problem, just jump in and do it. But if you're stuck, this process can a lot of times get you unstuck and get you moving in an efficient manner. Okay. The same thing with the givens. We want to write down the givens with symbols, and that can help us in picking out our equations. We pick out the relevant equation and solve. So this problem that I have up here on the board might be an example of what you could call a quick hitter. I believe that if you've put some time in this class, that you ought to be able to do something like that quickly and efficiently. I'd like you to try it really quickly. You might even do it on the side of your scrap paper. But I don't think it's necessary in a case like this to copy everything down, copy the diagram. Try to just use symbols, get it a shot, and we'll take it what it looks like. Actually, hang on, you guys. I'm really sorry. I missed one thing in the problem statement. Find the magnitude of the force of the atmosphere. Okay. Apologies about that. Okay, so this might be an example where someone's done these first 2 steps, okay? Obviously, if you know what to do, just jump in and solve. But I've written down the givens, okay? I have the area over here, 80 feet squared. I know that I'm thinking about atmospheric force over here, and I know the pressure of the atmosphere, and I want force. Now I'm trying to think, look, is there an equation we know that has F, A, and P in it? And I know you guys know it, but I want to pause and make sure you do it yourself as opposed to looking at the solutions or seeing what I do. Okay, it's pretty simple in this case. We have a single equation that has all 3 terms in it. Pressure is defined as force per unit area. So there we have it. And what we need to do is solve for force. Okay, so there is the work that I went through. Some people are having trouble with this step where we go from a definition that's a ratio and you're solving for some term within this ratio, in this case, force. So it may be helpful if you have ratios to use this triangle. Pressure is force over area. If I'm trying to solve for force, cover the F and I get pressure times area. There's the work. You do the homework, and you've done this many, many times where you've converted inches squared to feet squared, and you get a huge number. Okay, that is supposed to be a relatively quick hitter. And in part, I'm testing to see if you're efficient about how you take your information. And in part, you've got this process down of saying, hey, what are my givens? What is an equation? What's my want? What is an equation that has those things? That is essentially a fundamental of engineering education. You want to come out having that. The students I had a chance to talk to last semester, I saw a lot of improvement in this during the semester, and I encourage you to, if you're feeling stuck, take this approach. It's going to get better as the semester goes on. So going further, what we're going to do is use the linear momentum equation to calculate net force. And then once we have that number, we're going to do some useful other work with it. So here's a case like if this green line represents a control volume for a fan, and we go through and we use a linear momentum equation, and we get the net force on the air that is at steady state going through that fan is 80 pounds. Hey, that's interesting. Or how we're going to do that. How are we going to use that? How are we going to end up using the net force? Well, it's very similar to what was going on in physics 11A. I won't write this down, but let me just give you a reminder, okay? What if it was your job to do something very, very simple? Hang on for just a second, please. I'm going to get a different pen. Your job was to design a pulley system to make sure that that rope doesn't break. Well, you want a strong enough rope. And what you would probably do is take a look and say, well, hey, what's the biggest load I need to raise? Okay, and what actually is the maximum acceleration that someone might end up pulling that rope on so it goes up? And then you could do mass times acceleration, pardon me, not m dot, mass times acceleration to get net force. So let's say you go through that. Again, you're not writing this down, or you can if you want to, but I don't think it's essential. Let's say you go through that calculation and you get MA is equal to 40 pounds. So the net force, that would tell you the net force on this object is 40 pounds. Its mass times its mass and acceleration is 40 pounds. Okay, how do we use that? We do a free body diagram and use that to get forces. So a quick reminder, in this case here, if I took that object and do a free body diagram, okay, gives us all the forces on an object. All the forces on an object. So take a look at this mass here. What are the two forces? Well, there's weight down. Okay, and let's say we knew that. Let's say that this pulley system was going to do 120 pounds. You know, when you think about how much a person can conveniently lift or pull without straining themselves too much, around 100 pounds is not an unreasonable number. Okay, and then what's the other force on this object here? It would be the tension in the rope. Okay, and then on the side, I'll write down that we have net force is equal to 40 pounds up. Well, then what we do is we try to, from our free body diagram, I'm going to separate this a little bit, write an expression for the net force in terms of actual forces acting on the object, and make it equal to the calculated net force. So basically, please no need to write this down, but trying to express that idea, we'd say actual forces equals net force. Okay. So what are the actual forces? The tension up minus W. Maybe I could say actual net F equals calculated net F. That might capture a little bit more what we're doing. Obviously, I'm repeating something that you guys did in Physics 11A, so this is all old news. Just a reminder, the actual net force is the difference between the tension of the rope up and the weight down. Okay. And the net force, the calculated net force is 40. And then we can solve for the tension in the rope, 160 pounds. So we need a rope that can withstand 160 pounds. So once again, in Physics 11A, you did a lot of this, and some of you guys are, I believe it's Engineering 110, some of you guys are working more on getting better at this in more complicated situations. Well, we do the same thing here when we're talking about forces and fluids. The control volume approach with the linear momentum equation is first to figure out the net force using linear momentum, and then That is akin to this step right here. And then the next step is to do a free body diagram and think what are contributing to those forces so that we can write an equation. And we're going to work on that next step, the free body diagram. This next quick reminder may be worth your doing. I want to do a free body diagram of block A and block B that are resting on C, some concrete. And I want to use subscript notation. So if I had like F, B, A, that commonly is referred to as the force of B on A. Hey, in this class, you're welcome to use other sort of notation for force. But in this case, I'm going to use that on the board. So why don't you go ahead? Let's start easy. Let's go ahead and do a free body diagram of block A. Okay. And a couple of reminders. Free body diagram means isolate the body, separate it from everything else that's touching in the world, okay, and get all the forces acting on it. All right, working on A. Well, we're going to assume this is on Earth or we're on some sort of planet where there's gravity. So there's going to be weight down, which I could just denote W. If you wanted to actually stick with this notation, that would be the force of the Earth on A. Okay. Anything else that is pushing or pulling on A? Well, it's sitting on B, so B is pushing up on it. Okay. The concrete's not in contact with it. You might, I see some students that are tempted to say, oh, A pushes on B, so there's this one right here, force down. But again, in a free body diagram, we're just trying to do the forces for a body that act on that body, not what it pushes on others. So this should not be in that diagram. Go ahead and complete B. Go ahead and complete B. Okay, while you're working, you should have 3 forces when you're done with B. Okay, well, once again, it's on Earth, so there's going to be weight. So I got weight down. It would be a different weight than A. So I maybe could call this the weight of A, and this is the weight of B. Okay. A is sitting on B, so it pushes down on B. By the way, a force can be a push or a pull. A pull would be a force out. A push would be a force in, but push and pulls have the equivalent effect, so we can draw them anywhere. But I'm going to draw it up on top. You don't have to do that. Okay, and finally, looks like I got 2 forces down on A, on B, pardon me. What keeps it from falling? Well, that's the concrete, so that would be the force of the concrete up on B. Okay, then what we can do now that we have these diagrams is we can start putting numbers in on these forces and then either use balance, up equals down, or Newton's second law, net force equals MA, to actually work out the values for those forces. One other point, okay, how about these 2 numbers? What if this is 20 pounds? That means that, actually I should have, yeah. What if let's see, what if its weight was 20 pounds? Sorry, I'm fumbling a little bit. Well, then if A was 20 pounds weight, B would push up on A with 20 pounds. What about the force of A on B? It's also going to be 20 pounds. And this step right here, that's Newton's third law. Okay, if there's a force on A on B of 20 pounds, conversely, there has to be a force of B on A of 20 pounds. Okay, so we're going to go back to the nozzle problem and do a free body diagram of the fluid in the nozzle and try to get all the forces. This is a little bit different maybe than what you have done in Physics 11A or in dynamics. What are the different forces? Some similarities, some differently. So if this is a control volume and this is fluid inside a control volume, maybe it's air. What are some forces that we could think about that might act? Well, there's weight, once again, okay? This stuff has mass, so there would be a force down, all right? Okay. If the control volume has walls, so maybe if it's like a pipe, walls can actually exert forces, okay? If this were an inlet right here like this, and there were other fluid out here like this, well, this fluid could have pressure, and that pressure always acts into adjacent material. And so a fluid can push on a fluid. That's in fact true. So there can be pressure forces due to adjacent fluids, pressure forces due to adjacent fluids. Actually, sorry, I get a little bit tippy there. Of course, if we're doing something like a fan or a pump, then there are blades inside there that could do pushing as well. So we might consider the forces of blades, okay? And I'll just put that up there. We're not going to do that right now. We're going to keep things simpler than that. Okay. That's a pretty good list of some forces that you want to consider. All right, so first fluid free body diagram of the semester. We're going to do the nozzle, okay? And so, hey, what are we actually drawing? Well, if you remember, the problem was about the fluid inside the nozzle at any particular point. So what we might want to do over here, okay, is draw a trapezoid like that to indicate the nozzle, and that's the fluid in the nozzle at any point. Okay. What we're going to do is try to draw forces and just label them without putting numbers. And in this case, it was purely horizontal forces. So I encourage you to stop and think, can you think of any horizontal forces acting on water that are in that nozzle? All right, hopefully you came up with a couple, and you also thought about, hey, direction. And with vectors, with forces, we like to make the length of the force indicate how strong the force actually is. And here's some possibilities. Well, definitely that water that's in that nozzle at any point has weight. But if you recall, the problem that I had up earlier said, let's just figure out the horizontal forces in our free body diagram. Okay, so taking a look, is pressure would be pressure of adjacent fluids. So taking a look at our four surfaces, I've got a surface here, surface here, surface here, here, surface here. Okay, this surface right here represents the outer edge of that fluid. Is there any fluid adjacent to it that's exerting pressure? And no, there's not. And the same thing on the bottom. Okay, how about the fluid right here, just inside the entrance? Is there any fluid adjacent to it? Absolutely. There's the water behind it, and it is exerting pressure. And what direction would this water over here exert pressure on that fluid? It would be to the right. Okay, so there's going to be a force of pressure. You can use whatever notation you want, but I'm saying it's the force of the pressure. By the way, could we figure out a number for that? Well, we know this pressure, okay, and we know this inlet area, so we can come up with a number on that. Okay. Hey, we've got another surface to go. All right. Any fluid, any pressure, anything out here that would exert pressure at this point over there? Well, this is atmospheric pressure. Okay, and so basically, there's going to be the force of the atmosphere back on that. May be strange to think about, but for this fluid to come out here, it needs to be able to push against the atmosphere and emerge. So there's two forces. Okay, any other forces that would be acting on the fluid there that's inside the nozzle? Well, this surface right here, okay, actually touches the fluid, and so it's going to push on it as well, and it's going to push in just like any surface we would on a fluid. So there's going to be the force of this, you could maybe call it the side of the nozzle, and same thing down at the bottom. Okay. Now, I didn't dispel it all in great detail, but that's not a bad free body diagram. I'm just going to talk about that diagonal force for just a second. Okay, diagonal force. So this is the top one here like this. Okay, so it's pushing in. So this would be the wall up here, and it's pushing in. Maybe I could draw the fluid right there like that. Okay, well, it asked us to do just horizontal forces, and that's not horizontal. So what should I do with that? Well, basically, I could take this force and break it up into two components. Okay, one that is vertical like that pushes down, and the bit that pushes horizontally. Okay, and that would be true in this case. This wall here would essentially push back on the fluid. In the extreme case, I could actually make the wall the nozzle a very, very steep nozzle, and you could see that there would be this wall of the nozzle here like this would push back on the fluid that's entering it. It would hold it back essentially. So I can combine those two forces. They both have a horizontal component, and I could maybe call that the force of the wall. That's it. Horizontally, we have three forces. We have pressure pushing the water to the right. We have the atmosphere, in a sense, trying to hold it back. It's not successful. That water comes out. And we have the wall pushing back. So that's a complete free body diagram with all our forces, and we'll come back to that later on. All right, let's do our second free body diagram, and we're going to do the oil problem. So that would, remember there was a T and oil came down and it split with half going to the left and half going to the right. There was a pressure gauge on there at 30 PSI. And our control volume, or the volume that we did the net force analysis on using the linear momentum equation, was the oil inside there. So remember, free body diagram, it is not essential, but it is helpful to isolate the body that we're dealing with, okay? And we can brainstorm on the different forces. I'll get that list back up there. Weight, pressures, surfaces, okay? And also blades, maybe, might be a list, okay? And I'd like you just to brainstorm a minute and see, okay, could we come up with any forces that actually would be on that oil? All right, hopefully you got some arrows in there and have been thinking about it. I'll go through this list. Hey, would the oil in there have weight? Absolutely. Maybe if it's a really, really small T, it's not going to be that much, and we may be able to ignore it. Or if it's a big system, we would want to take it into account. So there's weight down. That's the weight of the oil. Okay. For the fluid that's inside there, the oil inside there, is there any adjacent fluid to it that could exert pressure forces? Well, absolutely, okay? Up here, the oil that's just outside there is under pressure, 30 PSI, and so it would push on the oil just right next to it with a pressure. So there'd be the force of the pressure here on that oil down, okay? All right, and of course that's going to be true over on this left side and on this right side. And so you would have a pressure force in there like that, and a pressure force in there like that. Okay. What we would probably do in this case is we would probably assume that these two forces are equal and cancel out, which would make sense if this was a perfectly symmetrical problem. Okay, are there any surfaces which actually is adjacent to the oil and actually push on it? And that's looking pretty complicated, but let's see if we can make it simple. There's this bottom surface that pushes up, this top surface pushes down, this top surface pushes down, this pushes left, and this pushes right. So wow, there's quite a few surfaces. But if you put it all together, what do you think the net force of the T actually is on the oil? Up, down, left, or right, okay? And you essentially have this oil rushing down, and then it splits and goes left and right evenly. So it should make sense to you that the T bottom surface is what does the bulk of the pushing and pushes up. So we could say that there's an overall force up on the oil of the T like that. Okay. So if we take a look at this, probably in our free body diagram, when we think about the forces, we're going to probably eliminate these two. And then we would get to work calculating. Could we calculate any of these? Well, sure, we could figure out the weight of the oil if enough information was given. There's enough information to figure this one out. And then the question is, how do we get the force of the T? Next, before we put it all together for fluids, let's do an object example where we remind ourselves how this actually works. So here's a very simple introductory physics object example where we have a 10 kilogram block. It's being pulled to the right. It's accelerating at 2 meters per second squared. The kinetic friction coefficient is 0.2, and we're supposed to figure out how big that pull is. Well, I know that many of you could do that in your head, but I just want to remind you and break it down. How in this case do you work out the net force? What is the free body diagram? And then once you put those two together, how do you write force equations to solve? I would like you to start really quickly with these two things and remind yourself how those work. All right, net force. MV out minus MV in. Well, that's what we're going to do if we do, actually I should put dots over this, probably. That's what we're going to do if we're actually doing fluids. But this is an object, so for objects, you do mass times acceleration. So two different versions of Newton's second law for objects versus fluids. This is an object, so we do mass times acceleration. So it'd be 20 newtons. Hey, force is a vector, so what direction is the net force on this object? It's to the right because it's accelerating to the right. All right, free body diagrams, okay? A little bit simpler in this case. So free body diagram, I isolate the body. I could do my free body diagram up here. But if I'm being meticulous, I do a separate body where I isolate it. And then forces, well, I'm going to call the P, pull to the right P. Okay, there's going to be weight down. There's going to be a normal force up. Okay, and there's going to be friction backwards, kinetic friction. Okay, so there's my free body diagram. All right, putting it all together, our force equations. Okay, we either say essentially if forces are balanced, that force in one direction are balanced in the other, and that's what we can do in this case. The normal force is equal to weight, so we could say that the normal force up is equal to the weight, and the weight is equal to mg. Okay, that's the y direction, and then the x direction, we don't say the pull is equal to the kinetic friction because there's a net force in the x direction, so we would say the pull minus the kinetic friction, okay, is equal to 20 newtons. And then we're on our way, okay? So with objects, we figure out the net force using Newton's second. We do a free body diagram, and then we try to combine the net force with the free body diagram to write equations. For fluids, we have a different way of figuring out the net force. But from there, it proceeds the same. By the way, a quick reminder, there's everything you need to actually finish this off is given because the force of kinetic frictions is usually modeled as the coefficient of kinetic friction times the normal force. So you could plug that all in there and calculate and get what that pull would need to be to make that block move the way you want it to move. So back to the nozzle problem then, trying to break it down the same way. So with the nozzle problem, the first thing we did was we thought about the water inside the nozzle and we figured out the net force on that nozzle, got a huge number. That was earlier during lecture, okay? Then a little bit after that, we did a free body diagram, and the forces we got on the water in the nozzle, we got a pressure force to the right due to the water adjacent to it. It's kind of like pushing that water. Any water that's in there has been pushed in. The atmosphere pushes back on it, okay? So yes, that water easily emerges and comes out in the atmosphere, but nonetheless, there is a pushback. And we got that the nozzle itself, that metal nozzle or whatever material it is, pushes back on the water. So those are the three forces, okay? And then just like the 2 kilogram block or the 10 kilogram block that we did a few minutes ago, I try to then write essentially what would be called Newton's second law, using the free body diagram, where I can say, you don't need to copy this down, but the free body diagram expression I get from the net force, from the net force I get from the free body diagram is equal to the calculated net force, okay? So we want to do positives minus negatives. Okay, maybe I'll change this to the force of the atmosphere. So we've got the force of the water pressure to the right minus the force of the atmosphere to the left minus the force of the nozzle on the water has to be equal to 96,659 newtons. Okay, and then if I pull back up the problem statement asks basically, can you figure out what the force on the nozzle of the water, the force of the nozzle on the water, magnitude and direction, and there's our equation right there. We have this, we just need to come up with these two numbers, and let's work on that really quickly. How about this force over here like this? How big is that? Okay, well, this is gauge pressure. So it's a gauge and it read 40 kPa. So it's a pressure above atmospheric. So this actual pressure over here, I'm going to round off a little bit, 40 kPa. Atmospheric is 101 kPa. So I'm going to call this 141, this pressure over here, 141 kPa. Okay, and then we really want to get good at using this relationship. If force is defined, pardon me, so I know it's a little bit hard to see down here. Bear with me for a second. If force is defined as pressure per unit area, then pressure is force times area. So basically, pardon me, if I'm sorry about that. If pressure is force per unit area, then force is pressure times area. So this FP over here, I'll write it in a different color so we can see it, is going to be equal to the pressure over here times the area. So pressure times area. The pressure is 141,000 newtons per meter squared. Okay, and then how do we get the area at this inlet? Well, we knew that this was we knew that this inlet was 10 centimeter diameter. So then we would do pi times 0.1 meters squared. Sorry about my writing. Pi times 0.1 meter all squared over 4. And if you take a look at those numbers, that's going to turn out to be newtons. So I'm going to give that a try myself and see how it turns out. Okay, and I would get a force there and I could carry it out. Okay, I'm going to stop there on that problem. I may have made these numbers a little bit unrealistic or sort of not working out the way I should, and I'm sorry about that, but I didn't take the time to do it. I'm doing the best I can to catch up. But you could see that you could calculate this pressure, you could calculate this atmospheric pressure, and then from there you could get the force of the nozzle on the water and finish that off. By the way, this on this lecture, I'm going to try to get it all done. So, you know, our class is usually 2 hours and 20 minutes. When I record the lectures, I go a bit less because I'm hoping that you guys pause and do any work yourself, so that it works out roughly equivalent to what lecture will be. But, you know, I really encourage you to sit and listen and compute for 2 hours and 20 minutes. I know you guys can do it, but sometimes it's productive to take a break. So we're getting close to the end, but at some point, hopefully take a break and refresh before you finish this off. Finishing off the T problem. So if you remember that, we had a T with a 6-inch inlet, and some engine oil came in and split. And if for the ending, to finish off the problem, the goal was to figure out the force of the T on the oil and also the force of the oil on the T. So we're trying to come up with numbers for those, magnitude and direction. So same procedure. We want to write an equation that says, hey, the actual forces acting on there, which came from this free body diagram, are equal to the calculated net force. And the calculated net force for fluids, we get in a different way by using the linear momentum equation. And that's what we got. We got that there was a force of 2.25 pounds up on that oil that's inside there. And there was no net force horizontally on that oil. It just came down and split. So everything in the x direction is our forces that we don't need to worry about. Okay, free body diagram over here. Taking a look at this free body diagram, we got 3 forces. This oil right here that's inside the T, there's an oil adjacent to it is 30 psi, so that pressure exerts on it. In addition, that oil had mass, 0.25 slugs, so there's weight down. And then the T was essentially pushing up on the oil, so those are the 3 forces. So if you want to pause, I think our goal basically is to come up with a number for the force of the T on the oil. You have everything you need there. I'll be working it out. Again, I encourage you to pause and see if you can work this out yourself. All right, so a first step, the net force is up. There's a net force up. I could put it over here to the side. That's not an actual force that acts on it, but in the net, all these forces push up. So the force of the T on the oil minus the pressure force minus the weight has to be equal to 2.25 pounds. And then I just need to figure out numbers for these 2 things and plug and chug and work that out. Do that yourself. Here's the pressure force, okay? A pressure force is equal to the pressure times the area. This is gauge pressure, and we want to figure out actually how hard is the actual push on that oil. So that would be 44.7 pounds per inch squared. The area of a circle is pi d squared over 4. In this case, we don't need to worry about that inches to foot squared conversion, and it works out pretty nicely. Hey, there's the number. Wow, that seems really, really huge. But if you think about it, 44.7 pounds per inch squared, that's a pretty significant pressure. And this is a pretty big T, 6 inches squared, so we get a lot of force. Okay, I want you to do the weight next. That's what I'm going to do. Weight, mass times gravity, okay? And when we're working in slugs, when we're working in English or BG units, this is 32.2. And unit-wise, we get a slug foot per second squared, which is a pound. And so that is down as well. So 8.3 pounds down, 8.31 pounds down. And now we got it. We can go back up to this equation and finish it off. The force of the T on the oil is 2.25. It's got to produce that net force. plus, move that weight to the other side, 8.1 plus this huge pressure force, 1263.9. Okay. And adding that all up, it's going to be in the 1,200s. I'll just get that myself really quick. Okay, actually, yeah, 1274, 1274. And what direction is that? That's up. So the force of the T has to push up on the oil. Well, how do we actually use this in engineering? A lot of times then we would think about Newton's third law. What is the force of the oil on the T? Okay, how hard is this oil actually here pushing on the T? And that would be Newton's, once again, that would actually be Newton's third law. If there's a 1274 pound up, there's going to be a 1274 pound force down, which is huge. What do we need to brace this T? Well, if it's being pushed down with that much force, there would need to be some bracing here, which would hold it in place. Okay, so one more example, and that'll do today. We'll try to put it all together. I'll get it on share screen, but before I do it, let me describe what's going on in this case. Perhaps a little bit artificial, but what we're going to have is we're going to have like a discharge pipe system, vertical discharge pipe, okay? And maybe there's some sort of piping here that brings fluid to it. And we're going to have some fluid go through that vertical discharge pipe and come out to atmosphere. And we're going to try to figure out, hey, what are the forces on that pipe discharge section? And what we can do is we can do a control volume. Think about the fluid inside that pipe. I believe I made it water, but I'll get it up there in just a second. Okay. And if we can figure out the force of the pipe on the water, where P would stand for the pipe, okay, or discharge pipe maybe I'll use. Okay. Then conversely, the force of the water on the discharge pipe would tell us how much force there is down on that pipe due to the water and allow us to think about bracing. So let me go ahead and get that up there. Well, first you might want to pause for a second and do that drawing because you're going to try to neatly add some information to that drawing and see if you can take yourself through it. Maybe pause for a second. I know it's very crude, but that'll get you going. Now let's go to, and we'll go to the problem then. So I'm going to go to share screen. Last example of the day. Okay, so you can read it yourself. And what I encourage you to do is get that information on your diagram in symbolic form. When you're working on test 1 on Tuesday, you don't even need to copy the diagram down on your paper. I'm just trying to be real, but if you want to make it very simple, and try to be real succinct. I'm working on it myself. Okay, hopefully you got that information down, and just thinking about what we're supposed to do, the first thing we're supposed to do is use the linear momentum equation to determine the net force, magnitude, and direction on any water that's in that discharge pipe. So let's go to the board and start working on that. Okay, so what we would do then again is we think of our control volume, which might be the interior of the pipe where the water is. So I'll do that as a dashed line, okay? And I got 4 surfaces, and we want to think, is there any momentum flow in, and is there any momentum flow out? I might want to write for part A, might want to write the equation I want to do. I want to do net force, okay? And I want to basically do m dot V out minus m dot V in. Okay, so I'll pause for a second and let you guys think about it. Okay, so there's no flow on this surface here. There's no flow on that surface there. We're working purely in the y direction, and we're going to figure out the net force in the y direction. By the way, this one's going to turn out just a little bit strangely, but it'll help you understand it. All right, so that what we want to do is we want to get the m dot, that we want to do the out minus the in, and we want to get m dot at the outlet. All right, well, hopefully remember this is actually the same sort of numbers as the first problem, just so we can make it go faster. The m dot in this case is going to be equal to flow, volumetric flow times density, and we got that early, 500 kilograms per second. Wow, that's a lot of water. Okay, that's a lot of water. All right, how about Vn? How about Vn? Well, we did that calculation earlier, and we got, when it was a horizontal, but the numbers are the same. We can get speed by doing volume by cross-sectional area, and this is 10 centimeters. We did that exact same calculation earlier, and I believe that turned out to be like 63.66 meters per second. Wow, that water is really flowing. Okay, let's say that those are the in numbers, 500 kilograms per second in, 63.66 meters per second in. How are the out numbers going to be? Well, if it's steady, and the problem did state that, then the m dot out would have to be the same. If it's the same diameter out at the outlet, the speed would need to be the same. So the numbers at the outlet are going to be identical. So taking a look at this, what are we going to actually get for part A? We're going to get zero net force on that control volume. So the answer to part A is zero. There's zero net force. And if you think about it, that's really similar to what you did in dynamics. If you have something moving along with a constant speed and it neither speeds up or speeds down, that's zero acceleration, so there's zero force. So the water in this discharge pipe is not being accelerated. There's zero net force. Okay, what was part B? Let's do a free body diagram of this and think about all the different forces that are actually acting on it. And of course, this case, we're just going to do vertical forces. So this represents the boundary of the water, and there's water inside there at any particular time. We're going to try to get four forces on there. And once part of the problem statement said that the walls of this pipe are rough. And what that's going to actually mean is there's going to be a frictional force. You can think about it as a frictional force, or sometimes that could be called a wall shear. So there's going to be essentially a frictional force on that water in there. So try to get four forces. Okay, so here are the four forces. By the way, I missed, pardon me, I was missing something in the problem statement. For a pipe of this size, I mean 10 centimeters, okay, is about 4 inches. That's a significant pipe. And if this pipe was maybe a foot long, this discharge pipe, that would be a non-trivial amount of water. So let's just make up a number and say it's 5 kilograms. There would be a force down on that water of weight, okay? It says that this water up here is under pressure, so the water just above it pushes down on it, and that's what that force of pressure, indicating force of pressure. At the outlet, there's atmosphere, so there could be atmospheric pressure right there like that. And then finally, this would stand for the force of the pipe on the water. I said that the walls were rough, and essentially there was shear at the wall, which results in force. The problem asked us to figure out the force of the pipe on the water, and that would be it. Okay, so that is part B, and then part C was actually asking us to solve for the force of the pipe on the water, and that's where we try to write Newton's second law, okay, which would be that net force that we get from actual forces equals the net calculated net force. Well, maybe we can be a little bit smarter on this. You know, maybe we might say up, okay, plus up minus down is equal to 0. But hey, this is going to be a case where forces up equal forces down. So taking a look at that, these two forces up balance that force down, those two forces down. So we could write an equation. I'm going to write this and erase it, but let me just get it up there. We could write an equation that said force of pipe on water, that's an up, plus the force of the atmosphere is equal to the force of the pressure that's down plus the weight down, okay? That's really good, and we could finish it off. But maybe we can be a little bit smarter on this. This is 25 kPa, and we're going to turn it into, we could turn it into absolute pressure by adding 101, an approximation for atmospheric pressure, okay? And that would be multiplied by this top area up here like this. Well, what's the pressure down here? That's the atmosphere, so it's 101. And so that would be 101 times the bottom area. And it was a constant air cross-sectional diameter. So basically what I would do here is I would be taking 25 and adding 101 times area. And here I would have 101 times area. I could just basically say, you know what I'm going to do? I'm going to make these, when I do pressure times area, here I'm just going to do gauge pressure and they're balanced out. So certainly we could do it that way. That might be a little bit to visualize. Maybe I'll work it out, just getting everything else out there. This is what I want to solve for. So I'm going to do the algebra and get it up there. Force of the pressure of the pipe on the water, okay, is going to be equal to the pressure force down. It balances the pressure force down, which would be 101 plus 25. I'm going to write it this way, okay? And that's kPa. So I would multiply that by 1,000 to make it into pascals, newtons per meter squared. And then this was a 10 centimeter diameter. So that would be pi times 0.1 squared over 4. Okay. Now I've got this term over here. I've got the weight, which would be 5 mass times gravity. So 5 times 9.81. Okay. And then minus, this atmosphere actually does provide some support to the water. So that would be 101 times 1,000. I'm sorry, my writings get a little bit small, but I think you can see what's going on. And then I would multiply it by pi times 0.1 squared over 4. Okay, and hopefully you can see that we can save ourselves a little bit of number crunching because I got a 101 here and a 101 there, so those are going to go away. So it's equivalent to what I was trying to say earlier. 25 times 1,000 is 25,000 newtons per meter squared times pi times 0.1 squared over 4 minus 5 times 9.81. Okay, and that computation is going to get us the force of the pipe on the water. So let me just crank through that. We're going to get a big number. 25,000 times pi times 0.1 squared divided by 4. Okay, all that turns out to be 196 newtons, then minus 5 times 9.81 is I get 147 newtons up. 147 newtons up. Okay. All right. So that was one part of finishing things off, and then the last thing was asked is, what is the force of the water on the pipe then? Okay. This water that runs through there, what force does it exert on the pipe? And that's Newton's third law. It would be opposite. So it would be 147 newtons down. Okay. So the pipe is being pushed down with a force of 147 newtons. That's a non-trivial force. I'm just trying to do a little quick conversion. That's like 33 pounds of force, and 33 pounds of force is not insignificant. That pipe might have weight itself, so we might need to do some anchoring up here to keep that pipe from actually disconnecting because the water is pushing hard down on it. Okay, well, good. Well, that's it. That is everything you're responsible for test 1. Monday's lecture, I believe, will be live. I think my dad's doing a lot better, and I'm not going to need to be with him on Monday morning. But Monday's lecture will be material that won't be on test 1. So some things that I recommend you do. I mean, I believe by right now you should be done with homework number 3. Take a look at the lectures that lead up to homework number 4 and get homework number 4 down. There will be a homework number 5. It will be very brief. I know this all sounds really intimidating, but if you just sit down and keep working through this stuff, you're going to get better and get more confident. I will have office hours where I can talk to some of you individually, and I will answer email questions. So that is it, and we'll be talking more soon. Take care.